Gee, what a welcome this is, I tell you. Music and dancing. So, this is my first time in Ukraine. So, thank you very much for having me. So, Mark Reinhold, when he was architecting Project Jigsaw, he gave 4 primary goals for Project Jigsaw. And the first one is to make the JVM smaller, in fact, the JDK smaller. Because many times, when you install the JDK somewhere or the JVM somewhere, you've got a lot of classes you'll never use, for example, Corba, Swing, and so on. And so the idea was to make it smaller for smaller computing devices. And this sounds really, really useful. But the more I think about it, the less use I can find for it. Because, well, the only thing you might be saving is disk space, and disk space is really cheap nowadays. You won't really save memory, I don't think, not that much anyway, because Java only loads the classes that you need anyway. So I don't know where that's going to help you. The second point was to improve the security. And that's what we're going to look at in more detail. And I think this is actually the big thing with Java 9 is improved security. So I'm going to show you a little bit about how to get around that, that annoying security, because we don't really want to have all the security stuff. So about 16 years ago, I went to an island in the Indian Ocean called Mauritius, and I taught a course there. And one of the things I wanted to know was, how do you use the security manager in Java? Now, I remember this very well because it was the last time anybody actually wanted to know how to use a security manager in Java, right? And it took me a long time to figure it out, and since then, no one's actually wanted to know or care. So we've had a lot of security in Java from the start, but we haven't used it. It's like, well, it's there, but let's not use it. So the second part is very important, and Java keeps on getting bad press about its bad security. So we need to find ways to make it more safe. And that's what Java 9 is mostly about. It's almost like a maintenance release to try and tidy up a big mess that was left behind. The third one is we want to enable application performance. Of course, they would say that, right? They're not going to say, hey, it's going to make it slower, right? So that to me is sort of propaganda. I don't know if it's really true. Some parts are faster, but not everything. Some things are just the same. And then the fourth one is to make it easier for developers to construct and maintain. Again, that's propaganda to me. It's like, yeah, obviously they'd say that. They're not going to say, we're going to make it more difficult for you to write Java code. Even though they actually do in some cases. So, what can we do with Java? Now, Java's always been supposed to be 100% secure, completely safe. You can't break anything. They had this whole thing with the sandbox. You can't get out of the sandbox. And in early versions of Java, if you want to do something very nasty, you had to go to JNI. And sometime along the way, they introduced this thing called sunmist.unsafe. Now, Simon this morning asked whether and if you used it, and not many admitted that they had used it. Now, what this does, sunmist.unsafe allows you to do all sorts of weird things. For example, you can throw checked exceptions as if they were unchecked. You can do things like create new objects without calling any of the constructors. You can allocate large blocks of memory natively, and then read and write. You can peek and poke into memory, any memory location, actually. You can do fences. And since Java 9, they've now added a new thing into sunmist.unsafe, which is kind of funny because the whole point of sunmist.unsafe or of Java 9 is to stop you using sunmist.unsafe. Right? Well, I'll show you that in a moment. And yet, they added a new feature into sunmist.unsafe. This sort of kind of doesn't make much sense. I'll show you how that works in a moment. So, I want to talk a little bit about how we got to even knowing about unsafe. And the big mistake that they made was calling it unsafe. If they'd called it com.corba, networking, boring stuff, no one would have looked at it. But you call it unsafe, and you're like, oh, this is cool. Like, for example, did you know that you can construct a string in Java 8 which shares a char array with somewhere else? There's a class called shared secrets. Right? So you can actually make a string that points to an existing char array. Well, I won't go into that because it doesn't work the same way in Java 9 anymore. But shared secrets sounds very enticing. It's like, I want to know how that works. Shared secrets, unsafe. Show me how it works, right? Now, in Java 5 and 6, there was this class called concurrent linked queue. Concurrent linked queue used something called a field updater, atomic reference field updater. So instead of having atomic references for the item and the next, those two fields, item and next, they had just the normal fields, volatile fields, of course, and then they had a field updater that will allow you to write and to read those values with, thread safety. So you can have compare and set and all these other things. And then in Java 7, they decided to change that. Instead of using atomic field updaters, because they are quite slow, they suffer from amnesia. Every time you call it, it forgets if you're actually allowed to do this. So they're checking in, can we do it, can we do it, can we do it? Now, and so that slows it down quite a lot. So in Java 7, they made it faster by using something called unsafe. And I think around about Java 7, people started realizing or noticing this thing called unsafe. And they started asking questions like, what is this thing over here where we're saying put ordered object, right? What is that all about? And so people started writing all sorts of very interesting code, single producer, single consumer queues and things like that, using unsafe. And we started using it more and more. Now, normally what you do is you would have your unsafe field. I'll show you how you get that in a moment. And you'd say compare and swap object on the object that you're trying to update and an offset, right? And the current value, the next value. And this is basically point arithmetic. So you have to specify the offset in your object of where the field is and then write it directly. So there's no protection at all. It's called unsafe for a reason. If you get this wrong, you're going to peek and poke into random places in memory. I've done that a few times. Usually it crashes, right? Which is okay. If it crashes, it's okay. But if you change random places, it's actually quite dangerous. So part of Java 9 was to get away from this peeking and poking from the use of unsafe. So they gave us something new called a variable handle or enhanced volatiles, which basically gives you something like an atomic field updater, but in a way that it checks up front whether you're allowed to do what you want to do. So what we're trying to do here is we're trying to update the item and the next. And so there's a var handle called item. And normally we name it as capital letters, the same as the actual field that we're trying to protect here. And then in the static initializer block, we would then say method handles.lookup, and method handles.lookup checks, or it gets a context for where you're calling it from. So that context can then check whether you've got the permission to get this var handle. All right, so you can see item equals l.find var handle. We're looking for a var handle from inside the class node called item, and the type of the field is object.class. Now, of course, you probably know that if you've got a generic type like e-item over here, that E is not a class. It's actually compiled as object.class, not E. So in Java 7, we saw that unsafe was used mostly inside Java util concurrent. That was like almost half of the uses were util concurrent. And of course, NIO as well. NIO uses it as well, but that's for the buffers, so you can't really get away from using unsafe there. In Java 8, we had more uses in concurrent. And this is where they said, we got to stop this reliance on unsafe. We need to use something else, which is more safe. So in Java 9, they decreased that quite substantially, right? No, wait, don't laugh too much, because don't forget that Java lang is all the var handles. And the var handles rely on unsafe to do the actual work. So in the end, it uses var handles. That's what it's going to be using. And var handles uses unsafe. So you get the same performance with var handles as you would get with unsafe. You don't have the cost of reflection when you're accessing, peeking and poking into fields anymore. Also, they've made the Java Naya, the buffers, a bit more efficient, which is why it's extended over here. So the line to look at is concurrent. And concurrent, we have actually achieved what we wanted to do, is to decrease our reliance on this thing called unsafe. So we don't want to use it anymore. Now, what we can do with var handlers is quite cool. We can do thread safe operations. So we can do, compare and swap. In fact, we can do a proper compare and swap, compare and exchange volatile. We can do compare and set. And then we can get and set the fields with different levels of concurrency, concurrent strength. So for example, get set plain is just like reading and setting a normal field. Get set opaque is slightly more strict. It basically gives you things like coherence, it gives you things like atomicity. And then you've got get acquire and set release. And these you can use if you've got, for example, a single producer, single consumer queue. You could use that. You can't use opaque for that, but acquire set release will work for that. And then get set volatile, that's the same as a normal volatile field. That's the strongest form of concurrent updates. And you've got fences as well. If you want to know more information, there's a document there that Doug Lee wrote with his friends. Now, I want to have a look at how we can use these things. First of all, there's this thing called long adder. Who's heard of long adder? Okay. Long adder is it's a special class to allow you to add up numbers very efficiently in a multi-threaded context. You see, if you have a synchronized field or synchronized method and you update it from lots of different threads, you have contention and you end up with poor performance. And similarly, if you take an atomic integer and you try and update it from lots of threads, you have lots of repeats, and these repeats also cost a lot. So we don't want to use either. Instead, what they do is they've got inside the long adder, it's basically a subclass of striped 64. Inside that, they've got cells, and the cells are associated with threads. So if the thread it updates his own cell, and this reduces the probability, reduces the chance of two threads trying to update the same cell at the same time. It's called lock striping, what we're doing here. And you start with a single cell, and as you get more and more CAS failures, compare and swap failures, it's going to expand the array until eventually you have 2 to the power of n, where n is, where the total numbers is a little bit bigger or greater, equal to the number of hardware threads in your system. So I've got 8 hardware threads in my laptop, so it will never make more than a cell array of 8. If I've got a 72 hardware thread server, it's never going to make more than 128 cells for that, because you only have 72 hardware threads, so you're not going to have clashes between multiple threads like that. So it's bound by that. What to do is to associate a cell with a particular thread. So the question is, how do they sort of decide which thread goes to which cell? Right? You could use a thread ID, but it suffers from an effect that you could get quite a few threads which are mapping to the same cell. So you want them distributed as much as possible. And so how do they do it? So something else I mentioned on the slide is that the cell objects are marked with contended, at contended. Now, at contended makes the cell objects bigger. Because they're bigger, they live by themselves inside a cache line, inside your level 1 cache. So they live without anybody next to it. So if you update the one cell, it won't update the others. It won't have to write out all the other cells as well. We'll get back to the contended in a moment. So threads are allocated permanently to a particular cell. The way they do it is actually quite strange. Right? You're going to probably think this is a bit of a hack. I hope you're going to think this is a hack. Let's go to something which seems completely different and not related to what we're talking about, which is something called thread local random. In the past, we used to use math.random to generate random numbers, but that stopped in Java 7 when they gave us thread local random, which is a much faster way of generating random numbers because it's all thread local. We don't want to have shared objects if we can avoid that. shared memory is far more expensive to manage than thread local memory. And in the first version of Java, of thread local random, each thread had its own instance of the thread local random, and it was stored, as the name suggests, in the class called thread local. Now, every time that you called current, it would have to do a map lookup to find the correct thread local for that thread. So in Java 8, they changed that. In Java 8, instead of having a thread local per thread, they actually store the fields inside the thread class itself. So the threads have moved, the fields have moved from a thread local variable into the thread. And again, there they've protected with @contended against false sharing, and we'll get back to that in a moment. Now, the striped 64 uses one of the fields of the thread local random in order to decide where or which cell belongs to which thread. Right? It's the probe field is used inside striped 64. So they wanted to avoid using unsafe. They really tried to not use unsafe anyway. And so they wanted to use var handles, but the problem is that var handles are only for your own class. So you can't see you can't see, for example, fields in other classes because you don't have the permission, especially if it's a private field, like probe, thread local random probe. So you can't see that, it's a private field. And so the question is, how do they do it? Now, they added a method called method handles.private lookup in. And this is, of course, quite fun, right? So they've opened up the API a little bit so that you can actually modify and read fields which don't belong to you, right? Just like deep reflection, like we've been able to do for many years with deep reflection. So here's what you can do. You can go to Java 9, and let's make a nice little class here saying hello. In fact, I'll do it like this, so everything's nice and big. And so ordinarily, if I try and get the var handle to the value field inside string, if I try to do it normally, method handles dot lookup dot find var handle, and I'll say that I'm looking for string on the string class, the field value, and what's the type of the array inside string? Byte array, exactly, it changed in Java 9, very good. So it used to be char array, now it's byte array, so just keep that in mind when you look at your object creation rate. Come on now. Byte array class. And so this, of course, could throw an exception. And you'll notice if you run this, that it fails. And it says, I'm sorry, but you can't do that because this class is not within your context, so you can't actually see that. And I need to just comment this out so that it compiles. So hopefully now it's going to complain. It says, sorry, but you're not allowed to do that. Illegal access exception. Members private. Okay? So what we can do is we can say here, method handles.private lookup in string.class, and we pass in the context method handles.lookup, and then we can say dot find var handle. So now we can actually get a var handle that points to a class that does not belong to us, that we should not have access to. So if we run this now, it warns us, but it does get the var handle. And then, for example, I can do cool stuff like value.get hello. This gets the byte array for hello. In fact, let's do this. Let's say .set hello, and we set it to the byte array that comes from cheers. Okay? And then we print out hello, and what do you think comes out? What do you think happens when you run this code? Okay. No, it doesn't work. Okay. And it doesn't work because var handles don't allow you to change a final field. Right? So this is a difference between var handles and reflection. With reflection, you can change final fields, no problem at all. With var handles, you can't reassign final fields, which I think is a great idea, actually. But what we can do is we can say, let's say byte array hello equals value dot get hello, okay, and then the cheers equals the cheers, and we need to do a casting here, and then after that we can say system.array copy from cheers position 0 to hello position 0 and cheers.length. And now when we run the code, what we've done is we've copied the contents of the array over to the other contents of the array, and we get exactly what you feared we would get in the first place of cheers. You see, what happens is in Java, when you've got constants like this constant string hello, it is shared, it's a shared object between multiple places. You end up with printing out cheers. Okay? And there's actually no way to prevent this because arrays themselves are not final. The contents of the arrays are not final. You can always reassign them. Of course, it does warn you, and these warnings are annoying, right? I mean, who likes to see warnings, right? So this is quite annoying, having all of this warning. So we can turn them off, right? And what we're saying is that we are doing something called deep reflection on some other class. So we're reading and modifying private data. And of course, you shouldn't be doing this. It's a bit like in Greece. I don't know if you've got this in Ukraine. In Greece, when you drive a car, it makes this really annoying beeping sound. Do you get that in Ukraine as well? It's like beep, 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 beep. And then after about 10 minutes of driving, it turns off, usually. I don't know what it is, but yeah, it's like that, right? These beeping noises. So these are those annoying beeping noises. So we can turn them off. We can basically say, we know that we're doing something we shouldn't be doing, but we're going to just say, we don't really care. And when we run it, oh, that's the wrong file. Let me try this one. So when we run it, we say, don't tell me about the problem. I'm going to just ignore it, right? And what we're saying is, my class is not part of a module. That's why it's an unnamed package. And I'm basically saying, even though I'm accessing private data, which I shouldn't be doing, I don't want to know about it. Right? So anybody from an unnamed package, unnamed module, can now go and access anything in Java base, and we won't know about it. Of course, this is to, don't take photos of this, please. You're not supposed to do this, right? And they tell us they're going to get rid of this in Java 10. So we'll see about that, because it's like Java programmers are like crack addicts, and he's saying, well, we're going to take away the crack next time. And they say, no, but we want to have this shared secrets and unsafe. I mean, in the beginning, they said, we're going to get rid of unsafe, and there was such an outcry that they still gave us unsafe. You can still get it, sun.misc unsafe. Now, you could do the same thing with JShell, right? Now, JShell is supposed to be for beginners in Java. Now, I've actually started recording a course that just uses JShell, because there's some parts which are quite handy for beginners. So, now, when you start it up, if you want like everything, all the classes available, you start up with Java SE. And then printing has some, helper methods to make printing easier, and then default is what you normally would start with. So you start it up, it starts up really quickly, like an hour later, and but it is compiling the entire JVM just about, and now it's available, and I can do stuff like 4 plus 5, which is like really cool, and then you can say, well, let's say 5 divided by 4, and it goes like 1, okay. Now I've really confused most programmers, or most beginners. Anyway, and you can actually use JShell to do some pretty cool stuff. Like, for example, I could say server socket let's say new server socket 8080. All right, what this does is it starts a new server socket, and it puts it into field 34, it's an anonymous field. Then I can say 34.accept, and now it's waiting for a network connection. Then I can say telnet localhost 8080, and I can, if we go back to the other window, it's now accepted a connection, a socket connection. And then I can say $35, and there's get input stream, and there's a new method in Java 9 called transfer to $35.get output stream, and enter. Okay, and then if I go to my other window, I can say hello, Kif, and it echoes back. How cool is that? Right? So this transfer to method is now there. I mean, I don't know if anybody's ever actually going to use it, but it's there now, right? But you can see, even you don't even have to have like methods, and you don't have to worry about semicolons and try catch and stuff like that. It's all pretty useful. Yeah, so for beginners, it's very handy if you actually know, if you already have the JDK in your head, and it's quite easy to use. But otherwise, it's not so easy. So anyway, let's shut this down. So Control C doesn't actually work. Control Z, yeah, that works. Okay, kill %1. Jobs, nah, doesn't want to die. %1, no. Okay. Okay, I best would kill it like this. Ah, now it's dead. Okay, fantastic. So now it's dead. Right. Anyway, that's JShell. And JShell looks like a great place to do sort of scripting. So if you've got a bash script, you can start with hash, exclamation mark, and whatever, and then you know that this is actually like an executable file. Well, you can do the same thing with JShell, but it's a lot more obscure. You basically start with, the first line will be a Java comment, then your $Java home /bin/jshell gives you the link to the JShell file, and then minus execution local. This is a funny trick in order to be able to return a number from the script, because by default, it always returns 0. And of course, if you're doing shell scripts, you want to be able to return a number other than 0 sometimes. And then minus startup default printing, right? And then $0 would be your current file, and then arguments. Now, unfortunately, you can't really pass in parameters into JScript, right? JShell. I don't know if it's JShell or JSHell. I'm not quite sure which one. But anyway, and then I've written a file called exit.jsh, and this exit.jsh looks like this. Where's my file now? No. There we go. So, come on. There. Just pull this up a bit. There we go. So there's a exit.jsh which just says /exit, which is like once I'm finished with my program. So this is pretty cool because I can then say hello world. Let's get rid of this for loop over here. And yeah, so with this first line, I can make a script which then returns something. System exit naught will return 0 at the end, so that means success. And so then I can say hello world, and if I have Java 9 running, or Java the field correctly, then very quickly it returns with hello world. Okay. Now, I know you're amazed at how fast Java is, but it does a whole bunch of work before it starts. And so this means that once you're running, it is the same speed as a normal Java program. So you don't have any of the scripting overhead once it's started up. You can see here that the real time is 3 seconds, the user time is 11 seconds. The reason is that it's doing lots of compiling of the abstract syntax tree in the background whilst it's starting up. And it's doing it in parallel, which is why the user time is so much bigger than the real time. All right. Now, where are we? I showed you some Java I/O. I've also got a little mini course on Java 9 using some of the Java 9 tricks. And if you subscribe to that, it's only valid until the end of my talk, which is another 20 minutes, I see. I must hurry up here. So if you subscribe to that, then you'll get my newsletter, You'll get this course for free, which normally sells for 60 euros. And yeah, I'll show you that link again at the end if you're not quite there. Okay. So, something else which is quite fun, right? You can map a file in Java into memory. And then when you change the file, it changes, well, if you change the memory, it changes the file automatically. You don't have to go and change that yourself. You don't have to flush it out or anything like that. So we can do that quite nicely, and I'm going to do this within IntelliJ, and we're going to first do it in Java 8, and then we'll do it in Java 9 afterwards. So this is our Java 8 version. And let's try and find, this is the one. Okay, so this is what the code will look like. Buffer test. You can use a try with resource, of course. We make a random access file. Raf equals new random access file with the file name and read-write format. Now, this throws exceptions. We're going to just rethrow the exception in a moment. Then we say raf file channel fc equals raf.getChannel. So we get the file channel. And then from the file channel, we get a map byte buffer. So ideally, I would want to put the map byte buffer in here. I'd like to say mapped byte buffer buff, bug is actually the right word, I should call it bug, not buff, equals fc.map. Now you specify the read-write mode and the starting position and the length of what I'm mapping into memory. But it doesn't work putting it into the try with resource, because mapped byte buffer is not auto-closable. You can only put classes inside the try that are auto-closable. So you can see we can map a map byte buffer, but we can't unmap it. So this has to go inside here. And I've got one bracket like that. So you can map it, but you can't unmap it. So the question is, how do you unmap it? So if I say buff.put int, for example, 42, into this, I'm going to map it, but to unmap it happens automatically. What happens is that the map byte buffer creates a phantom reference called a cleaner, and this cleaner points to the memory location and the whole infrastructure, the direct buffer, which needs to be cleaned up at the end. All right. So what does this give us? Well, if we run this code, we don't actually see that it's not being unmapped. But if we pause for a while after running it, so if here I say console.wait for enter, this is sort of a little class I wrote with just basically does system in and reads from it. And so I'll do it twice, .wait for enter. Okay, so let's run this. And I'm going to launch JVisualVM and see whether or not the buffer is released. Now, JavaDay is a tool which we used to have in the past, in Java 8 and before that. It's quite useful. It's gone now, but we used to have it. And you could connect to do a whole bunch of profiling and memory dumps and so on. And you can see one of the plugins you can get is something called buffer pools. So it shows you that you've got 1,000 bytes as a map byte buffer. Now, you can see if you look at the code that I've actually exited this try with resource, but I'm actually waiting for a system GC so that this map byte buffer can be unmapped for me. It won't be unmapped without a system without a garbage collection event. And so you can force that by saying perform GC, which will do the GC, but you can see that I'm still pointing to it. And this is because the buffer is actually still being kept alive. So you could change that. You could actually rewrite this a bit and define this, declare it above, and after the first console, in fact, let's do it over here. Let's say, once we're done, we can say buff equals null. So if you set it to null, then it's no longer strongly referenced, and now it can actually be garbage collected. So let's run this again. Wait, the other one is still running, I think. Yeah, let's stop this. and restart it. And now the second time around, when you connect to it, let's connect to buffer test. It's still there, right? It's still using 1,000 bytes. But if I now press enter, it's set it to null. It's still mapped to 1,000 because the GC hasn't run yet. If you now run the GC, then it clears it off. It's gone, right? And so there's always a challenge because we don't want the garbage collector to run. That's the whole point. We're trying to avoid the GC from running, right? And if we do that, then we're going to have all these buffers which are not being cleared. So a very popular trick with which we could shoot ourselves in the foot in the past was to do the following. Now, don't do this, right? I'm just showing you what people used to do, but you shouldn't actually be doing this. So they used to do this. They used to say, let's take the buffer and cast it down to direct buffer, which is a sun.nio class, so you shouldn't actually be using it, and then call cleaner, which gives you back the cleaner, and then call clean on that. So we're actually forcing the clean to happen. Now, if you run that again, wait, the other one's still running. Let me stop this one. So let's connect again. We can see the buffer pool is there. And now, if I press enter, it's going to manually unmap that buffer. Now, this is a very, very bad idea. It works, right? But it's a very bad idea. Because if you accidentally use it after that, then, well, anything could happen, right? This might fry my machine. Hopefully it won't, but let's just see what happens if I say put int 57 right, afterwards, and I run that. Then you can see here, enter, whoop, and now I've got a segmentation violation, and as a result, I've got a core dump, right? Which is what you should see, but of course it's all pretty ugly, so you can really hurt yourself with these things. Now, why am I talking about this? Well, actually in Java 9, they've got a new way of doing it, which is with unsafe. So there's a method in unsafe which does this. It does the same thing as we did now. It basically casts it down to direct buffer and then uses that, which is incredibly dangerous. And I'm not quite sure why that is. As I mentioned, JVM is gone in Java 9. So if you've been using that for analyzing performance problems, well, too bad, it's gone. You can still get an older version from GitHub and install that separately, but it's not part of your standard JDK. Also, the -x1hprof is gone. That's another thing which we used a lot for analyzing problems. But you've got Java Flight Recorder, which is being open sourced around about March, April next year. That's the plan. So even though they're taking away one toy, they're giving us another toy which is much better. So I'm really looking forward to that. As I said, the plans, the people I've spoken to said March, April sometime, we should be able to get that for free. Now, I mentioned before how we did deep reflection. What happens if I want to use a class that belongs to Java base or some other package, but which hasn't been exported to my package to be used? For example, let's say that I want to make a particular field contended. Now, when I make it contended, it means that my field will be made bigger. It will allocate more memory so that there won't be any other objects living in the same cache line with my object. So it'll be living by itself, and I won't get the effect of false sharing. Now, if I compile this class as it is, Java's going to complain and say, I'm sorry, but you don't know what you're doing, which is most likely true, and you shouldn't be doing this. So here's my highly contended. And you see, it's JDK internal, and of course we shouldn't be using classes from JDK and K internal in our classes, but well, the alternative is quite complicated. To make your own fields, to implement this yourself, have a look at the black hole in Java micro-benchmarking harness to see how it can be done alternatively. But this is quite complicated, and so the question is, how do you do this? And if I try and compile this, it's just going to complain and say, well, this is internal, it's not visible, you're not allowed to do this stuff. So the way to do it is to give my package access inside there. Now, at the moment, all my classes are on the unnamed module. You can actually, you would normally put your classes into modules as well, but here you can say, even though this public class, because it's a public class, it's not a private class, this public class, even though it's public, it's not normally accessible because of modules, so we can say, let's add it to the module definition by saying add exports. And after that, it becomes part of we can compile without a warning, and then we can use it, if you want to use contented, you say minus XX minus restrict contented to do that, to use that as well. So add opens allows you to access private fields, private members of classes that don't belong to you. Add opens implies add exports, and then add exports is only for compile time to allow you to compile against public classes, and they promise they'll get rid of this in the next version. So, they said that before. They really are threatening us. We will get rid of it. Anyway. Some other ways you can shoot yourself in the foot is with the new Stream API. They've added some functions, take while and drop while, which on the surface look brilliant, and something which people ask, why wasn't this there from the beginning? But it becomes really interesting when you work with parallel streams. Now, I've had some cases where I tried this out, and in the serial stream it worked perfectly. Parallel stream, it boom, gave an out-of-memory error. So be careful with this. It's no longer the case where the parallel and the serial stream are equivalent. That's changed. They've also changed garbage collectors. So in Java 8, they deprecated incremental CMS, and they got rid of that completely in Java 9. It's no longer there. But in Java 9, they've also deprecated CMS. So if you're not using G1 yet, you need to move forward to using G1. And G1 is going to be the default instead of the parallel throughput collector that we have as default in Java 8. Now, the propaganda from Oracle is that G1 is incredibly easy to configure. All you do is you set the maximum pause time, then you set the maximum heap size, and you're done, right? The reality is a bit more complicated, and you can get a very big improvement if you configure it more thoroughly. So just be aware there's new things coming on that. Now, one last thing. Let's say that I've got big integer. Now, we all know there's this class called big integer. And big integer at the moment is rather annoying because, let me get it off the Java 8 version. Whoa. Big integer is rather annoying because big integer's got this nice method called square, but square is private, so I can't call it. I like square, but I can't call it. So let's say that I want to use square, but it's private. What do? Well, it's quite easy. You say, right, then you go to your package over here, and you put Control V. All right. Then you go to square, and here's square, and you make it. Oh, you can't make this one public. You've got to go in here. Square. And you make it public, right? So now I've copied and pasted it into my own class, made it public. Of course, you need to make sure your license is all okay, but I've now changed the interface. I've made it public. Now, if I go back to my big integer test, because I've set up IntelliJ in this way, I've basically moved this to the top. If normally it would complain and say you can't access it, right? This is what you normally see. So, but if you move the module to the top, then you can actually see it, right? Now you can't run it, right? Because when you run it, it's going to say no, this is private. You can't see it. Okay, so it's going to complain about that. In fact, complains about a whole bunch of things here. It's like just really in a bad mood, right? In Java 8, it was quite easy. In Java 8, you just compile it. Once you compiled it, you'd start up with -x boot class path and put it at the beginning of your boot class path. Then it used your modified big integer. But here that is a bit more involved. So what you need to do is there are 3 steps. The first thing is you need to compile the hacked big integer version. So this is how you do it. I'm going to do this copy and paste because I can't remember all these settings. You basically compile it first of all, which is going to be like this. So you first have to compile it with a patch module. This creates a patch for the Java base package, right? So now I've got a package with my own big integer patch. The next step is to compile our code against the patched big integer. So this is now my code compiled against the patched big integer. And then the last step is to run against the patch as well. Now this used to be basically one step in Java 8. In Java 9 you can still do it. This is now square, 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 square. But it's a lot more involved. So I think I've given you enough ways to shoot yourself in the foot. Do you have any questions? Yes, sir. Okay. Okay. Stream will take a while.
Yeah.
Whoa.
It's now seems fine. I have a question about parallel streams and take while.
Yes.
I just got one use case in my mind. Can this be used like when you have infinite stream and for example to stop processing at some time?
Yeah, that's quite interesting. So you have to always worry about if you don't have parallel.
Yeah.
Then it's okay. You can say take while the value is less than something. But the moment you've got parallel, then it confuses everything. Because one of the threads then might find that the other ones have to cancel as well. And it's all pretty complicated because, for example, with the fork join framework, there's no easy way to cancel a task that you've asked to do. It's very difficult to cancel once you've got the parallel stream running to cancel that.
So it's really unsafe, like, yeah?
Yeah, in fact, the Java docs warns you against using this for parallel streams. They say your mileage might vary.
Okay, thanks.
Anything else? There's a
Yeah.
question over there. I'm already scared about this question. Ah.
Hey,
Whoa.
oh, that's quite extensive. The question is related to security. So currently we have a security policy where we can probably make some changes and forbid reflection and so on and so forth.
Yeah.
Of course, in this case, our enterprise applications, which are using reflection quite extensively, will not work. But how can you, well, is there, for instance, for var handle, also policies which can forbid you to go there?
Yeah, of course. So your private lookup in is going to by default.
For instance, yes.
Yeah, so that one will need to have the support of the security manager. So if I, for example, set a security manager, then my hack won't work, which is this hello thing here. If I say system.security manager, new security manager, it won't actually run. Or I have to give it explicit permission to be able to do that. Let me get rid of this big integer again. Let me try do it anyway. No. Sorry. So you'll see now a security exception. And I've got to undo all the stuff I've done. Okay, there we go. So you'll see security exception. So this is the same as you had with normal deep reflection. So Java 8, you also would have gotten a security exception if you tried to do this type of modification.
Yeah, but can you scroll a little bit farther than that? Suppress. The question is if there is specific policy for the private access for var handle?
No, I don't think so. I think
So
this is just a normal...
Because with that, I can switch off all the reflection, which kind of not what I wanted.
Yeah, that's so basically, once you open up this thing with the var handles, you're probably going to open it up for everybody, for also other deep reflection. Yeah, good point.
Okay.
But, you know, who uses security managers anyway, right? That's the problem. That's why we have so many holes. All right, we're done. Thank you very much for inviting me.
Thanks a lot for an awesome talk.